Welcome to the Deep Dive, where we transform complex information into clear, engaging insights. Today, we're tackling a really fundamental chapter from Silberberg and Amorphous' chemistry, the molecular nature of matter and change. Just imagine standing near Kilauea in Hawaii, you've got molten lava, solid rock, gases all coming out, then that liquid lava hits the ocean and boom, steam, volcanic glass shards. Lays, they call it. In that one moment, you're seeing all three states of matter, gas, liquid, solid, and crucially, the changes between them happening right there.
Yeah, that's a fantastic image. It really captures what we're diving into today. Intermolecular forces, liquids, solids, and phase changes. Our goal here is to, well, unpack the invisible forces that shape the world we see. Why ice floats, how your phone screen actually works. We want to give you a solid handle on these core chemistry ideas, but without needing diagrams.
Okay, so we'll start with the basics, right? The forces and energies dictating whether something's a solid, liquid, or gas. Then we'll look at heat, how it drives these changes quantitatively. After that, we'll break down the intermolecular forces themselves, and then dive into liquids and solids, especially water, which is fascinating before we wrap up with some cutting-edge materials. Sound good? Let's get started.
Sounds great. So basically, whether something is a gas, liquid, or solid, it really boils down to this constant tug of war between two kinds of energy. You've got potential energy. Think of that as the attractive forces, the electrostatics pulling molecules together. And then you've got kinetic energy, the energy of motion, always trying to push those molecules apart, make them move randomly.
Right, so it's attraction versus motion. Now, you mentioned forces pulling molecules together. Could you clarify the difference between the forces inside a molecule versus the forces between molecules? That seems key here.
Absolutely crucial. The forces within a molecule, like the strong covalent bonds holding H and O together in H-arrow, those are intramolecular forces. They define the molecule's chemical identity. Water is water, chemically, ice, liquid, or steam. But the forces between different water molecules, those are the intermolecular forces. They're much weaker, but they're the ones that dictate the physical states, solid, liquid, or gas.
Okay, got it. So as we go from gas to liquid to solid, how does that energy balance shift? Less motion, more sticking together.
Exactly. Moving from gas to liquid to solid, the attractive potential energy becomes more dominant, and the disruptive kinetic energy decreases. In a gas, particles are zooming around, far apart, high kinetic energy. Easy to compress, flow freely. Think atmospheric gases mixing. In a liquid, they're closer. More attraction, less freedom to move. They take the container shape but have a surface. Harder to compress than gas, flow slower.
Right, and in a solid.
Solids, well, particles are pretty much locked in place, just vibrating. Strong attractions rule. They have their own shape, own volume, almost no flow, very hard to compress. Think about rock layers staying put for ages.
And these energy differences, they directly explain the phase changes, don't they?
Yeah.
Add heat, increase kinetic energy, particles break free. Remove heat, they slow down, attractions win.
Precisely. And every phase change involves heat transfer and enthalpy change. It's either endothermic, absorbing heat to pull molecules apart, like melting or boiling, or it's exothermic, releasing heat as molecules get closer and attractions form, like freezing or condensation.
Let's take melting and boiling. Melting ice needs some energy. Boiling water needs way more energy. Why is that vaporization so much more energy intensive?
That's a really key point. Melting, or fusion, just needs enough energy to loosen the molecules from their fixed solid structure so they can flow past each other. The forces are weakened, not totally broken. Vaporization, though, requires enough energy to completely overcome essentially all the intermolecular attractions holding the liquid together, letting molecules escape entirely into the gas phase. They have to break completely free.
Ah, okay. That makes sense. Like sweating, it cools you because evaporating that water takes a huge amount of heat energy away from your skin.
Exactly. It's a very effective cooling mechanism precisely because water's heat of vaporization is so high thanks to those intermolecular forces we'll get into.
Okay, let's quantify this heat thing. You mentioned heating or cooling isn't always smooth. Can you describe this heating-cooling curve idea?
Sure. If you plot temperature versus the heat you're adding or removing, you see distinct segments. Within a phase, say, heating liquid water from 20 degrees C to 80 degrees C, the temperature rises. That added heat increases the kinetic energy, the motion of the molecules. But during a phase change, like when ice is melting at 0 degrees C or water is boiling at 100 degrees C, the temperature stays flat, completely constant. All the heat energy being added goes into changing the potential energy, breaking or forming those intermolecular attractions, rearranging the molecules, not speeding them up.
So plateaus on the graph mean phase changes are happening.
Yeah.
Interesting. And this relates to equilibrium too, right? Especially in closed systems.
Yes, absolutely. In a closed container, like a sealed flask with some water, phase changes become reversible. You reach a dynamic equilibrium. What that means is water molecules are constantly escaping the liquid surface to become vapor.
Vaporization.
And at the same time, vapor molecules are hitting the surface and returning to the liquid phase.
Condensation.
Right. At equilibrium, the rate of vaporization equals the rate of condensation. So the amount of liquid and vapor stays constant. Even though molecules are constantly moving back and forth, it's dynamic.
And the pressure from that vapor at equilibrium, that's the vapor pressure, isn't it? What makes it higher or lower?
Two main things. First, temperature. Higher temperature means more molecules have enough kinetic energy to escape the liquid surface. So higher temperature, higher vapor pressure. Second, the strength of the intermolecular forces. If the forces are weak, molecules escape easily, high vapor pressure. If the forces are strong, like in water, molecules are held tightly, low vapor pressure.
Okay, so diethyl ether, weak forces, high vapor pressure, water, strong forces, low vapor pressure. Makes sense.
And this temperature-vapor pressure relationship is actually described mathematically by the Clausius-Clapeyron equation. It's pretty useful.
Useful how? Does it let us predict things?
Yeah, it links vapor pressure, temperature, and the heat of vaporization. So if you know the vapor pressure at one temperature, you can calculate it at another, or you can figure out the heat of vaporization, or even predict the boiling point.
Ah, the boiling point. So that's directly connected to vapor pressure then.
It is. A liquid boils when its internal vapor pressure becomes equal to the external pressure pushing down on it, usually the atmospheric pressure.
Which means boiling point isn't always 100 degrees C for water.
Exactly. Go up a mountain, like in Boulder, Colorado, the atmospheric pressure is lower. So water boils at a lower temperature, maybe 94 degrees C.
Yeah.
Food takes longer to cook.
And a pressure cooker does the opposite. Increases pressure, raises the boiling point, cooks faster. Clever. And weaker intermolecular forces mean a lower boiling point too, right?
Yeah.
Less energy needed to get that vapor pressure up to atmospheric pressure.
Precisely. Less energy to break free. Solids also have equilibria, by the way. The melting point is where solid and liquid coexist in equilibrium. And some solids, like dry ice, solid CO2, can sublime go directly from solid to gas if their intermolecular forces are weak enough relative to the vapor pressure they generate.
Okay, to visualize all this, chemists use phase diagrams, like a map for phases.
Exactly like a map. It shows you which phase, solid, liquid, or gas, is stable at any given combination of temperature and pressure. For most things, like CO2, you see solid at low temp pressure, gas at high temp low pressure, and liquid sort of in between.
And this explains dry ice. At normal atmospheric pressure, the phase diagram shows CO2 goes straight from solid to gas as it warms up. It sublimes. You need higher pressure over 5 atmospheres to get liquid CO2.
Right. Phase diagrams also show a critical point. Above that specific temperature and pressure, you don't have a distinct liquid or gas anymore. You get a supercritical fluid. It's fascinating stuff. It flows like a gas but dissolves things like a liquid. Supercritical CO2 is actually used commercially to decaffeinate coffee or extract oils.
But water's phase diagram is weird, isn't it? That solid-liquid line slopes the wrong way.
It does. It slopes backward, negative slope. That reflects something incredibly unusual. Solid water, ice, is less dense than liquid water. Almost everything else is denser as a solid.
Why? What's happening with the molecules?
It's those hydrogen bonds again. In ice, they arrange the water molecules into a very specific, open, hexagonal lattice structure. Think of a snowflake symmetry. This open structure takes up more space than the more jumbled arrangement in liquid water.
So ice floats, which is unbelievably important.
Foundational for life as we know it. If ice sank, lakes would freeze solid from the bottom up. Aquatic life couldn't survive winter. The density changes also drive water circulation in lakes, mixing nutrients, and freeze-thaw cycles breaking rocks apart that helps make soil.
Wow. It really shows how these tiny molecular details have massive consequences for the whole planet. It's a perfect example of what the textbook calls chemistry's central theme, right? Macroscopic world reflects the microscopic.
Exactly. Now, to really get these intermolecular forces, we need to think about how close molecules can even get. There's this idea of the van der Waals radius. It defines the closest approach between atoms on different non-bonded molecules. It's always bigger than the radius involved in covalent bonding within a molecule. It's sort of the personal space boundary where these weaker intermolecular attractions start to matter.
Okay, so these intermolecular forces are weaker than chemical bonds. Let's break them down. What kinds are there? You mentioned ion dipole.
Right, ion dipole forces. That's when you have an ion, a charged atom or molecule interacting with a polar molecule, one that has a positive end and a negative end, a dipole.
Like salt dissolving in water. The positive sodium ions attract the negative oxygen end of water, and negative chloride ions attract the positive hydrogen ends.
Precisely. Water molecules surround the ions, pull them apart. That's why water is such a great solvent for many ionic compounds.
Okay, what about forces between neutral but polar molecules?
Those are dipole forces. The positive end of one polar molecule attracts the negative end of another. They tend to line up positive near negative. The stronger the molecular dipole, generally the stronger these forces are, and you usually see a higher boiling point as a result.
But then there's a really special case, right? Hydrogen bonds. They seem to come up a lot, especially with water.
They do. Hydrogen bonds are like a super strong type of dipole interaction. They're very specific. They happen when you have a hydrogen atom that's already covalently bonded to a very electronegative atom, specifically nitrogen, oxygen, or fluorine, NO or F. That hydrogen is then attracted to a lone pair of electrons on another NO or F atom nearby. So you need that H bonded to NO or F and interacting with another NO or F.
Why NO or F specifically?
Because they're small and very electronegative. This makes the bond very polar, leaving the hydrogen atom with a significant partial positive charge and making it strongly attracted to the lone pair on the neighboring NO or F. This is why water, ammonia, and hydrogen fluoride, HF, have boiling points way higher than you'd expect based on their size. It explains water's unique properties, DNA's double helix structure, protein folding. It's incredibly important.
Okay, so we have forces involving ions and permanent dipoles. What about nonpolar molecules? Or interactions induced by fields?
Good question. Even in a nonpolar atom or molecule, the electron cloud isn't perfectly static. An external electric field, maybe from a nearby ion or a polar molecule, can distort that electron cloud, push the electrons slightly to one side. This creates a temporary induced dipole. The ease with which the electron cloud can be distorted is called polarizability.
And bigger atoms are easier to distort, more polarizable.
Generally, yes. If the electrons are further from the nucleus, they're less tightly held, more easily pushed around. This leads to things like ion-induced dipole forces, an ion creating a dipole in a nonpolar molecule, or dipole-induced dipole forces, a polar molecule inducing one. These are important when things dissolve.
But what holds purely nonpolar things together, like liquid nitrogen or solid wax? They don't have ions or permanent dipoles.
That brings us to the universal force. Dispersion forces, sometimes called London forces. These exist between all particles, atoms, molecules, polar or nonpolar. How do they work? Well, electron movement is random. At any given instant, the electrons in an atom or molecule might just happen to be more on one side than the other. This creates a fleeting, instantaneous dipole. This temporary dipole can then induce a dipole in a neighboring particle. For a split second, they attract each other. These flickers of attraction happen constantly across all the particles.
So even nonpolar molecules feel this attraction. And it adds up.
It really adds up, especially for larger molecules. While dispersion forces are the only force between nonpolar molecules, they contribute significantly even when other forces are present. Like in water, maybe 25% of the total attraction comes from dispersion. Their strength depends heavily on polarizability. Bigger molecules, more electrons, generally stronger dispersion forces. That's why boiling points tend to increase down a group in the periodic table, like for noble gases or halogens.
Does shape matter too?
Yes. A long, skinny molecule like N-pentane has more surface area contact with its neighbors than a compact, spherical one like neopentane, even though they have the same formula. More contact means stronger total dispersion forces, so N-pentane boils at a higher temperature.
Okay, that covers the forces. Now let's look at liquids specifically. They flow, but the forces are still pretty strong, right? Leading to unique properties.
Exactly. Liquids are this interesting intermediate state. One key property is surface tension. Think about a molecule in the middle of the liquid versus one at the surface. The one inside is pulled equally in all directions by neighbors. But a molecule at the surface only has neighbors below and beside it. There's a net inward pull. This makes the surface molecules pack tighter and causes the liquid to minimize its surface area like it has a skin.
Which is why water forms droplets and bugs can walk on it, because water has strong hydrogen bonds, so high surface tension.
Precisely. Water surface tension is remarkably high. And yeah, that skin is strong enough to support water striders. It also explains why adding soap, a surfactant, helps cleaning it lowers the surface tension, allowing water to spread out and wet surfaces like greasy dishes more effectively.
What about liquid climbing up thin tubes? Capillary action.
Right, capillarity. It's a result of the interplay between cohesive forces, attractions between liquid molecules themselves, and adhesive forces, attractions between the liquid molecules and the surface of the tube. If adhesion is strong, like water to glass, both polar, forming hydrogen bonds, the liquid climbs the walls, pulling the rest of the liquid up. It creates a concave meniscus curved downwards in the middle.
But mercury in glass does the opposite, right?
Yeah.
Convex meniscus.
Yes. Mercury atoms have strong cohesive forces, metallic bonding, amongst themselves, much stronger than their weak adhesive forces to glass. So mercury pulls away from the glass, cohering to itself, forming a convex meniscus curved upwards. Capillary action is vital. Think plants drawing water up from the soil through narrow vessels in their roots and stems.
And the last liquid property, viscosity. Resistance to flow.
Exactly. Viscosity is basically fluid friction. It comes from intermolecular forces hindering the molecules' ability to slide past each other. Stronger forces generally mean higher viscosity. Temperature plays a big role too. Heat things up, molecules move faster, overcome forces more easily, so viscosity decreases. Think how easily hot maple syrup flows compared to cold.
Does molecular shape matter here too, like with dispersion forces?
It does. Long, chain-like molecules can get tangled up, increasing viscosity. Compare something like glycerol, with lots of hydrogen bonding sites in some length, to ethanol, which is smaller. Glycerol is much more viscous, like syrup. Motor oils use long-chain hydrocarbons for this reason.
Okay, let's talk specifically about water. It seems like almost every property we've discussed is somehow special or extreme for water.
It really is unique, and it all comes back to that simple H0 molecule. Bent shape, highly polar OH bonds, and the ability to form up to 4 hydrogen bonds with its neighbors in a tetrahedral arrangement.
Its solvent properties, for instance, it dissolves so many things.
Its polarity and hydrogen bonding make it fantastic. It dissolves ionic salts using ion-dipole forces, as we said, and it dissolves other polar molecules, like sugars or alcohols, that can hydrogen bond with it. Life depends on water being this universal solvent for biological processes.
And its thermal properties are way off the charts, aren't they? Specific heat and heat of vaporization.
Incredibly high.
Yeah.
All that energy needed to break hydrogen bonds means it takes a lot of heat to raise water's temperature, high specific heat capacity, and a huge amount of heat to vaporize it. High heat of vaporization.
Which is why oceans moderate Earth's climate so well.
Right. They absorb and release heat slowly, preventing drastic temperature swings. And as we mentioned, why sweating is so effective for cooling our bodies. Without it, the heat from our metabolism would cook us very quickly.
Its surface tension and capillarity are also high, which we saw is important for insects and plants.
Vital. High surface tension lets things float, creates habitats. High capillarity lets plants pull water up from deep underground, especially crucial during dry spells.
But the density thing is maybe the weirdest and most important. Ice floating.
Absolutely the most striking anomaly. That open, hydrogen-bonded crystal structure of ice makes it less dense than liquid water. We already touched on the consequences. Lakes freezing top down, preserving life. Density changes, driving leak turnover. Freeze-thaw cycles, creating soil. It's fundamental to geology and ecology.
It truly hammers home the connection. Molecular structure dictates macroscopic properties and behavior.
Definitely. Now, shifting focus slightly to the solid state in general, solids aren't all the same, are they? There's crystalline versus amorphous.
Right. Crystalline solids have that beautiful long-range order. Think salt crystals or quartz. Their atoms, ions, or molecules are arranged in a repeating pattern called a crystal lattice. The smallest repeating unit of this lattice is the unit cell, like one tile that repeats to make the whole floor pattern.
Amorphous solids, on the other hand, lack this long-range order. Their particles are jumbled, more like a frozen liquid. Glass, rubber, charcoal are examples.
For crystalline solids, we can actually figure out the structure, can't we? Using X-rays.
Yes, X-ray diffraction is a key technique. X-rays have wavelengths similar to the spacing between atoms in a crystal. When X-rays pass through, they get diffracted by the atoms in a pattern that depends on the crystal structure. Analyzing that pattern lets us map out where the atoms are. It's how we know the structures of metals, salts, even complex molecules like DNA.
So based on what's at the lattice points and the forces holding them, we get different types of crystalline solids with very different properties.
Exactly, you can categorize them. Atomic solids, just individual atoms like noble gases frozen at low temps, held by weak dispersion forces, very low melting points. Molecular solids, whole molecules sit at the lattice points, held by intermolecular forces, dispersion, dipole-dipole, hydrogen bonds. Properties vary a lot. Ice versus wax versus sugar, but generally softer and lower melting points than ionic or metallic.
Okay, then ionic solids.
Cations and anions in the lattice, held by strong electrostatic attractions, ionic bonds, hard, brittle, high melting points, good electrical conductors when molten or dissolved, but not as solids because the ions are fixed. Think table salt, NaCl.
Metallic solids.
Metal atoms at the lattice points, but the valence electrons are delocalized. They form a sea of electrons moving throughout the crystal, holding the positive metal ions together. This sea explains their excellent electrical and thermal conductivity, their shininess, luster, and why they're malleable, can be hammered into shape, and ductile, drawn into wires.
And the last one, network covalent solids.
These are like giant molecules. Atoms are joined by covalent bonds in a continuous network throughout the entire crystal. Because covalent bonds are very strong, these solids are typically extremely hard and have very high melting points. Carbon is the classic example. Diamond has each carbon bonded tetrahedrally to 4 others incredibly hard. Insulator. Graphite has layers of covalently bonded hexagons, strong bonds within layers, weak forces between, so it's soft, slippery, and conducts electricity within the layers due to delocalized pi electrons.
That difference in conductivity, metal versus diamond versus graphite, how do we explain that more deeply? You mentioned band theory.
Right. Band theory extends molecular orbital theory to the huge number of atoms in a solid. When many atomic orbitals combine, they form continuous bands of molecular orbitals. You get a valence band, which holds the valence electrons, and typically a higher energy conduction band, which is usually empty.
And the gap between them is key.
The energy gap between the valence and conduction bands determines conductivity. In conductors, metals, the valence band is either not full or it overlaps with the conduction band. There's no energy gap or it's negligible. Electrons can easily move into empty energy levels within the bands and flow freely when a voltage is applied.
Okay, so easy electron movement equals conductivity. What about insulators?
In insulators, like diamond or glass, there's a large energy gap between the full valence band and the empty conduction band. Electrons don't have enough energy to jump that gap, so they can't move freely. No conduction.
And semiconductors are in between.
Exactly.
Yeah.
Semiconductors, like silicon or germanium, have a small energy gap. At room temperature, a few electrons have enough thermal energy to jump the gap into the conduction band, allowing a small amount of current to flow. Importantly, increasing the temperature gives more electrons enough energy to jump, so conductivity increases with temperature opposite to metals.
Fascinating. And this ties into superconductors, too. Materials with zero electrical resistance.
Well, superconductivity is a more complex quantum phenomenon, not fully explained by simple band theory. But yes, these materials allow electron flow with absolutely no energy loss, usually at very low temperatures. Discovering materials, often complex ceramic oxides, that can superconduct at higher temperatures, like near liquid nitrogen temperature, 77 K, was a huge breakthrough. It holds immense promise for things like lossless power lines, powerful magnets for MRI or maglev trains, and faster electronics, though making them practical is still a challenge.
This really leads us into the whole field of advanced materials, doesn't it? Where science is designing materials with specific properties.
Absolutely. Material science is where chemistry, physics, and engineering meet. We're learning to control structure at the atomic and molecular level to get desired functions.
Like with semiconductors, we don't just use pure silicon, right? We dope it.
Right. Doping is intentionally adding tiny amounts of purity atoms to a semiconductor crystal to drastically change its conductivity. Add an element with more valence electrons than silicon, like phosphorus from group 15, and you introduce extra electrons into the conduction band. That's an N-type semiconductor, N for negative charge carriers.
And if you add an element with fewer electrons, like gallium from group 13.
Then you create holes vacancies where electrons should be in the valence band. These holes act like positive charge carriers. That's a p-type semiconductor, P for positive. Putting n-type and p-type materials together creates a p-n junction. This is the fundamental building block of almost all modern electronics, diodes, transistors, integrated circuits. It can control current flow, amplify signals, switch circuits.
And things like LEDs, light-emitting diodes, are based on this too.
Yes. When electrons and holes recombine at a p-n junction under the right conditions, energy is released as light. The color depends on the semiconductor material and its band gap. That's how we get efficient red, green, blue LEDs for displays, lighting, traffic signals. It's revolutionized lighting technology.
Amazing. What about other advanced materials? Are there materials that are sort of between liquid and solid?
You're probably thinking of liquid crystals. They're fascinating substances. They can flow like liquids, but their molecules maintain some degree of ordered arrangement, like in a solid. Typically, the molecules are long and rod-shaped. They can align themselves in different ways: parallel, nematic, layered, smectic, or twisted cholesteric. This order makes their properties, like how they interact with light, depend on direction.
And we can control that alignment.
Yes, often with an electric field. That's the basis of LCDs, liquid crystal displays, in your watch, calculator, TV, or phone screen. Applying voltage changes the molecular alignment, which changes how light passes through polarizing filters, creating the image. They also have applications in high-strength fibers like Kevlar, or even temperature sensors based on color changes.
Okay, let's wrap up with a really cutting-edge area: nanotechnology.
Working at the scale of billionths of a meter.
Exactly. Nanotechnology deals with materials and structures typically between 1 and 100 nanometers. At this scale, properties can be dramatically different from both individual atoms and the bulk material. Quantum effects become important. Like you said, aluminum nanoparticles can be explosive, while foil is stable.
How do we even work at that scale?
Tools like the scanning tunneling microscope, STM, and atomic force microscope, AFM, have been key. They allow us not just to see individual atoms, but even to manipulate them, to build structures atom by atom or molecule by molecule. Nature, of course, has been doing nanoscale engineering forever through self-assembly processes.
What are some examples of nanomaterials? Oh, there are many exciting areas. Quantum dots are semiconductor nanocrystals whose color depends purely on their size, used in displays and biological imaging. Nanocomposites mix nanoscale components into bulk materials to enhance properties. Think stronger, lighter plastics, or self-healing cements. We mentioned synthetic bone grafts. Carbon nanotubes have incredible strength and electrical properties, huge surface area potential for hydrogen fuel storage, stronger materials, new electronics.
And nanomedicine.
Huge potential there. Designing nanoparticles to deliver drugs specifically to cancer cells, developing ultrasensitive biosensors to detect disease markers much earlier, using nanoparticles that heat up when exposed to light to kill tumors. It's a rapidly evolving field.
So from the basic push and pull of energy-defining states of matter, through the specifics of forces like hydrogen bonds, to designing materials atom by atom, we've covered a lot of ground.
We have. We've seen how these fundamental intermolecular forces govern everything from why water boils at 100 degrees Celsius to why ice floats, to the complex behavior of liquids and solids, and even how the most advanced technology works.
It's really quite something. Understanding these tiny interactions gives you such insight into the big picture, the world you experience every day. Hopefully digging into this helps you connect these ideas when you see them in your studies or just in the world around you.
And it really makes you think, doesn't it? As our ability to understand and manipulate matter at this level keeps improving, what kinds of new materials and technologies, things we can't even conceive of now, will emerge?
A fascinating question to ponder. Thank you for joining us on this deep dive into intermolecular forces, liquids, solids, and phase changes. We hope it's giving you a clearer, perhaps more engaging perspective on the molecular nature of matter. From the Last Minute Lecture team, until next time, keep exploring.